Assalamualaikum. Now we continue on our chapter 2, homogeneous semiconductor, focusing on compensated semiconductor and degenerate semiconductor. Before we start with the new topic, let's recap on what we have learned previously. Extrinsic semiconductor is a semiconductor that has impurities added intentionally to increase the conductivity. There are two types of doping, one from group 3 and one from group 5, creating a p-type and n-type semiconductor respectively. For this new topic, we are going to learn about the dopant concentration that can influence the conductivity of the semiconductor and understand the physics of compensated semiconductor and degenerate semiconductors. We have learned that extrinsic semiconductor is a type of semiconductor that has impurities intentionally added in it to increase the conductivity. Extrinsic semiconductor can be divided into two types, which are compensated and uncompensated semiconductor. Uncompensated semiconductor has only one type of doping. It is either donor dopant or acceptor dopant. Donor dopant will create n-type semiconductor and acceptor dopant will create p-type semiconductor. Compensated semiconductor has two types of dopant in the semiconductor. If donor dopant concentration is higher than that of the acceptor dopant, the material will become n-type. If acceptor dopant concentration is higher, then the material will become p-type. Why do we need to have compensated semiconductor? This figure here shows a basic device fabrication step, which is the diode. A diode is made of n-type and p-type semiconductors, creating separate areas of n-type and p-type. So, in order to fabricate a diode, we have a p-type silicon as the base, or we call it substrate. And then we create an n-type areas on the p-type. So, although the n-type region seen here is denoted as n-type, but actually this region is a compensated semiconductor region because it has two types of doping in that area. Thus, to create this n-type region, the donor concentration Nd must be larger than that of the acceptor type Na, making it to be effectively an n-type semiconductor. In device development, we may need to have a conductor as connector or other important roles, and at the same time, we need to minimize the usage of other metal materials to prevent from contamination in the IC chips. Thus, we use doping to increase the semiconductor conductivity to a very high level, almost similar to metals. Conductivity in a semiconductor is proportional to the carrier concentration, and carrier concentration is directly proportional to the doping concentration. By doping the semiconductor using an extremely high doping concentration, the semiconductor will have enough carrier concentration that will allow them to have a similar characteristics as metal. The semiconductor that has an extremely high doping concentration is called the degenerate semiconductor and denoted by the small plus sign. For example, in this figure, the N plus and P plus regions are degenerate semiconductor regions. What happens when the doping is extremely high? In a normal doped semiconductor or non-degenerate semiconductor, dopant atoms are far apart enough to assume that there is no interaction between the dopant atoms. But when the doping is too high, the states of the dopant atoms for the higher donor levels can overlap if the doping concentration is high enough because dopant atoms are close enough together. This will create a dopant mini-band as shown in this figure. In this example of an N plus material, a donor mini-band is created and at the bottom of the conduction band is lowered. This will result effectively in a reduced energy gap. This phenomena is called impurity-induced band gap reduction, with the difference value is denoted as delta Eg. So how do we identify if the material is a degenerate or non-degenerate semiconductor? From calculation, degenerate semiconductor is defined when the value of Ec minus Ef for n-type or EF minus EV for p-type is smaller than 2.3 kT. Here K is the Boltzmann constant with a value of 8.62 times 10 to the power of minus 5 electron volt per Kelvin. T is 300 Kelvin, or kT is 0.0259 electron volt. Thus 2.3 kT is 2.3 times 0.0259, which is equal to 0.05957 or 0.0596 electron volt. So if EC minus EF is smaller than 0.0596 electron volt, the material is degenerate n-type material. If EF minus EV is smaller than 0.0596 electron volt, the material is degenerate p-type material. In summary, there are two types of extrinsic semiconductor. One is compensated semiconductor, which has two types of doping. For compensated semiconductor, if the donor dopant or Nd is larger than acceptor dopant or Na, the material is n-type and the electron concentration is Nd minus Na. If Na is larger than Nd, it is a p-type with the whole concentration is Na minus Nd. For a degenerate semiconductor, it is considered as a degenerate semiconductor when the doping is extremely high. The degenerate semiconductor has similar characteristics such as metals, which means that it is highly conductive. For a degenerate semiconductor, for n-type, EC minus EF must be smaller than 2.3 kT, and for p-type, EF minus EV must be smaller than 2.3 kT.